Good afternoon, everyone. My name is Kevin Burt, and I'm with Samtec. So what we're talking about today is really about midboard optics. And where we are coming with midboard optics is we are coming from the commercial space. So you've heard from SOSA about how we're wanting to be able to move quicker with designs and be more flexible. And that's one of the advantages of where we are in terms of the commercial market space. And so a lot of lessons we've learned as we move into the area that you guys know so well. And some of them have been painful, some of them have been easy, but just wanting to talk about some of the challenges, and especially around the firmware. So in terms of the wiring diagram, we're talking about the optics, which is that component there. So we've heard from Reflex about their midboard optics, and we're very similar to them. One difference that we have is our connector system, and also Samtec as a both optical and copper company is able to do copper or optical in the same connector set. And the recent acquisition of Reflex by Smiths, now suddenly you see another company who's getting the ability to do both copper and optics. It's something you're seeing happen in the market a lot more, both commercial and mil-aero as well. So the critical thing is we have the ability to put optical or copper in the same system. And so where we see that being useful is, well, the fundamental thing that, if you've worked in optics, you know that optics are going to be 3 to 5 times more expensive than copper. So it gives you design flexibility that if you're going at a lower data rate or shorter distances, then use the cheaper option. It's going to work. If you have to go the longer distances, or if you need to think about noise isolation, then optics is the way forward. One of the critical things is because we come from the commercial base, our volume is so much higher. And the other areas that we play are in generally where FPGAs are involved. It could be automated test equipment, 5G, or different applications like that, supercomputing, ASIC emulation and verification, industrial and medical. And the critical thing about the volume is, at the end of the day, volume, as everybody knows, helps bring the price down. It gives improvements to manufacturing efficiency, and in terms of semiconductors, it also helps you with reliability models and understanding the strengths and weaknesses within a design and a product. So one of the things that for people who are new to optics, it's quite eye-opening seeing what's inside a transceiver. So we've got the connector system. We need to get the electrical signals from the board to the optical cable. So with Samtec, we use a 2-part connector system, and the idea for that is that you can get the high speed as close to the ASIC as possible. We heard earlier that signal integrity is critical. One of the things about Vita is we have the shorter traces, so it makes life easier there. But you can still get as close as possible. The other connector is used for power and communications, and more importantly, it stops the whole thing from being a diving board. Obviously, we care about shock and vibe and the more rugged environments, and so that's one of the other purposes of the connector. And it's not just Samtec who is doing this type of connector system. You may have heard of COBO, Consortium of Onboard Optics, which is aimed much more at the data center, but they do the same idea there. After that, we've got the PCB. Everybody knows and understands the PCB. And then we've got the optical ICs. So one of the questions earlier was, what's the difference between passive and active? So really, passive optics is just like a standard copper cable. You put something in at the one side, in this case optics, you get optics out the other side. An active cable, you're going to put electrical in and get optical out, or optical in and electrical out. So you now have the ICs that take the signal from the voltage that we're used to to an electrical signal that is more suited for the optical chips themselves. That's the VCSEL, which is a laser, and the pin, which is the opposite of a laser. It detects light and converts it back to electricity. We also have a microcontroller, and we're going to be coming back to that later. Just because we need to control, we need to monitor, similar to the voltage diagnostics for the power supplies that we heard about earlier. We also have an optical lens because we need to get the light from the laser to the fiber or vice versa. We have the fibers themselves, and then we have a heat sink on the top. So as with anything that has a power supply, we're dissipating voltage, we're dissipating power, and so we need to get the heat out of the part. In the grand scheme of things, all the optical devices are not generating much power. But we're pretty darn small, and so the power density is significant. And so the key about this, and Reflex are similar, is a modular design. It means that we can change the optical chips, the electrical chips, to get different functionality, be it number of lanes or data rate. With our design, we also get the ability to change the heatsink and the fiber and the optical connectors. And that's not saying that Reflex don't. Reflex and others, they have similar mechanisms as well. The technology is all very similar. So one of the things that we do different is PCIe. One of the things that people talked about earlier was a system that's PCI, but then needing to bridge to something else, be it Ethernet or whatever, to go longer distances. PCIe is actually capable of going longer distances. It's just most people don't design their ICs or their silicon around it, or they don't set it up. I mean, why worry about latency if you're just going to be inside something this big, or maybe a server, or maybe a Vita card? So PCIe, not bridging to another technology, another protocol, can help with latency. And one of the questions earlier was about the latency of a redriver. It was actually something I looked at for PCIe. And so if you know your standard PCIe add-in card, like a standard graphics card, there's actually not much difference between having no chip, having a redriver, and having a full CDR. And I say that because we're generally talking the hundreds, the 500, maybe picoseconds, maybe up to 1 nanosecond for the latency through those chips. Whereas the latency through fiber is about 5 nanoseconds per meter. So by the time we start going hundreds of meters, the latency of a chip doesn't really come into it. There's so much more variability in the fiber. Other things that kind of came up earlier was we're talking about the heat sinking and water cooling. You can see the different heat sink types for the air or the a secondary heat sink coming over the top. We see a lot of people using liquid cooling for those. And in the commercial market, we just had a new return problem where our parts came back and they're not working, it's a major quality problem. Yeah, commercial parts don't work well when you spill water from your cooling system all over them. And it was really admirable because the customer tried denying it for a good 2 weeks until we had all the pictures kind of showing all the growths that were happening. Obviously with conformal coating and the like in our market, it's not going to be the same issue, but water cooling does leak. On the fibers, there was the question about the 72 fiber connectors. And so the way the standard fibers work is it's glass, polished glass, pushed against solid glass. And so that's how you get your low insertion loss. You're wanting no air to cause reflections. Fresnel reflection, on a dark night when you look out a window and you see what's inside because it's lighter than outside, 4% of light will bounce back from an air glass interface, and that happens. So by getting rid of that air, you get a low loss. Well, how difficult is it to get 72 fibers, 6 rows of 12, to all have really good compression? Not that easy. You need a big force, and then you can also get higher insertion loss. And so the market is looking at things like having non-contact ones where they're specifically designed to have lenses that there's coatings to prevent reflection, but it means that you're not bothered about dirt or dust or other things that can get in the way of the signal, which is really important if you're in the desert or mud or anything like that. So there's definitely opportunities there. They haven't really been looked at extensively in all the environmental conditions that we care about with mill standard and the like, but there's a lot of opportunity there. And then just the other one, with just coming from the commercial background, data centers, they all care about plenum grade cables that you can put through air ducts and other things, but generally you've got PVC as your outer coating, the blue, that blue there. So that's PVC, and so most military applications, it's a no way, and so it's just another thing to think about. Roadmap. So really what we're talking about here is you start with commercial, you then, for us, you then extend into the harder temperature range, and it's one where all semiconductors, especially lasers, Arianis law, that the cooler you can make it, the longer the lifetime. So as you go to the wider temperature ranges, you have more challenges with both operation and reliability. Adding to that, firmware security, which we're going to come back to, but it's been touched on in some of the earlier presentations. And then finally, protective coatings, conformal coatings, the things that are expected in the market for fungus, for salt fog, for dust, for salt, 100% humidity. The things that the commercial world doesn't care about. Really what wanting to talk about is firmware security. And really it's firmware security coming from the commercial world. For a lot of companies here, the idea of your software, your firmware team coming in the morning, opening the safe, getting the hard disk out, plugging it in the computer, programming on a standalone machine, and then putting it back at the end of the day is normal. But in the commercial world, it's all about networks, about having everything available. Maybe you've got a PLM system which is managing everything. So your engineering teams, your customers, your suppliers, your manufacturing all have access to one location where everything's located. So it's very easy, depending on your cybersecurity for the company itself, for somebody to come in and get all the information possible. So we're all aware about viruses, ransomware, phishing, general leaks. I work for a commercial company. That means I'm going to get my standard phishing security check, every couple of weeks to see if I'm going to click on the link. It's not a mindset. And so we get a horrible level of people clicking on the link and then IT going, don't do it again. And in 2 weeks' time, it happens again. But it's a different mindset coming from the commercial world. We've already talked about, I can't remember what you talked about, the Lenovo supposedly having extra chips. Well, actually, if you go back further, back to 2000, Nortel got some of their systems into the White House. What nobody realized at the time was that the Israelis, the Mossad, managed to get one of the Israeli companies to put a backdoor into their chips that Nortel put on their board. And so it is highly speculated that Israel had access to White House communications going back that far. So it's not new. It happens, and it'll continue to happen. From my side, in terms of FireFly, so with Lenovo, they were saying, oh, it's a chip the size of a surface mount capacitor, and it was able to store and then transmit information later. Well, I invite any foreign company that can find space on mid-board optics to put these extra chips in, because there really isn't much space there. But it leads to the challenge, the questions that, how can your component become a weakness in terms of, could you get information taken away from a secure system on it? Or, more importantly, could it be hacked to damage, to break a system? There was a mention of the I2C bus earlier. I2C, you've got ground, you've got data, and you've got a clock. Everything is controlled by the host, the system, the master thing. But any component can go, I need to think about that, and then hold the clock low. And with no clock, there's no communication. So all you need to do is hack into the firmware of one of these devices and just say 2 hours after turn-up, you hold that clock low and you never release it. Well, now you don't have a communication bus. Maybe it's not important for the optics, but you often share the communication buses, and so there's something else on there. So in terms of market requirements, one of the things for security is no customer or end system can write to non-volatile memory. That is, if you turn the part off and back on, it should go back to standard default settings. You shouldn't be able to write secrets or anything that's a part of a classified system on there that can be removed. Similarly, the day of your EEPROM is gone, it's the micro. You don't want to be able to come in and change the firmware. So you've got a system with pluggable optics. You can easily pull those out and put them in the shredder, and you don't have to worry about that. With a system with midboard optics on it, your midboard optics are generally going to be stuck there when you remove it from a classified area. And so you need to be able to erase that. You've got the standard NSA arrays, DoD arrays, other ones, to try and make sure that the memory is fully sanitized before it's removed. But then the other one in the commercial world is, we've got new features. Do you want firmware access? Well, do you want upgraded firmware? Well, that is going to be a direct write to memory. And so no longer can you get there. I was talking about access to systems. You've got Git or something similar where you put all your historic, all your work in progress with lots of comments, if you've got decent programmers. I'm not. So that you can actually fully understand what every part of the code is doing. Another thing that we have is, as I said, the field upgradable firmware. And so you have a bootloader that's kind of like a backdoor that prevents the app, that gets in the way before the application runs. And generally, if you've got access to the bootloader, it's kind of like the BIOS. You have the ability to say, let's boot from that USB drive I just plugged in the front. It gives you the opportunity to do things that you don't really want to do. Quite often the micro, and when I talk about micro, we're not talking about the luxury of the micros that people get to use, maybe an Intel or something like that. We use very simple ones because we just don't have the space or the power dissipation in which to do anything complicated. So we're short on memory, we're short on size, we're short on things, but nearly every micro has the erase all function. And one of the things you find after you erase all is that it doesn't actually erase all most of the time. So that's another gotcha you have to start thinking about. And the other one with commercial first approach is, you want your firmware to be robust. Firmware doesn't like erasing itself. So if you're trying to sanitize the part, generally the firmware will stop you from overwriting it. So you really have to change the way you think about firmware. There's lots of advantages to doing commercial first. You've got volume, you're kind of ahead of the military requirements. We're already looking at 56 gig PAM4 in the data center. It's standard on FPGAs now. We're seeing 112 gig PAM4 happening in copper. And so, the military applications, defense security, aren't there yet, generally lag a generation behind. But it also leads to the security challenges, some things that were touched on earlier, the component selection, firmware development, do you have manufacturing backdoors to get in? Things that, it's the mindset difference between there and where we need to be.